So today I first want to show you the slides that I couldn't show you yesterday because my computer refused to cooperate with the projector. And then afterwards we're going to immediately dive into neutrino oscillations, but we're going to do that on the blackboard again. Now very quickly regarding yesterday, this is the more beautiful version of what I had tried to draw on the blackboard. That's the Katrin experiment in Karlsruhe, not far from here, which aims to measure neutrino masses directly by using the kinematics of tritium beta decay. I was asked after the lecture yesterday why specifically tritium, and I should have said that, of course. The advantage of tritium is that the Q value of the decay is very low, so only 18.6 keV. And that means the relative precision that you need in order to measure the neutrino mass is quote, quote, only order 10 to the minus 5. For most other nuclear decays, the Q value is much larger, so you need a much better relative precision in your spectrometer. So here, this section here, this is what I called yesterday the windowless gaseous tritium source. That's where the tritium is basically flowing through this pipe that does not have a window on the end, at the end, so that the electrons can drift out freely. Then there is here the small pre-spectrometer, and this here is the main spectrometer. What you see here around it is coils to shape the electric field, and then there's also lots of wires inside to shape the electric field. And finally here in the end is the detector where those electrons that have passed through are detected. It's a segmented detector because the position where the electrons hit the detector also contains information on their energy. This is, to give you a sense of scale, this is the size of the main spectrometer. So you see it fits onto a ship, but onto not much else than a ship. This is also the reason why, even though this spectrometer, it was made here in Deggendorf by a company in southeastern Germany and is running in Karlsruhe, but there was no way of transporting it there directly. So the way to do it was you put it on a ship, you go down the Danube River, you go through the Black Sea, you go through the Mediterranean, up the Atlantic coast, up the Rhine River until you get to Karlsruhe. There was, at some point, there was a plan of transporting it with a blip, so you know, an airship, a Zeppelin, but the company that operated that thing went bankrupt beforehand. And this is then what it looks like on the few kilometers it had to take from the Rhine to Karlsruhe. And this is one of the most iconic pictures of the experiment, and that's why we generally agree that this can't be scaled any further, because that would mean tearing down people's houses. Because it just fit through with a few centimeters to spare on either side. They had to take down the street signs and everything to make room for it, but you clearly can't make it any bigger. This is what it looks like, or looked like, from the inside during installation, and this as well. So here you still see the structure where people are standing, and it also gives you a size of scale. This was one of the first Katrin results. There are now updated ones, but what you basically see here as a function of energy, the count rate. So you see here this falling tail of the spectrum ending right at the end point. It's a little bit smeared out here due to finite experimental resolutions. And there's no indication of a non-zero neutrino mass yet, which allows them to set limits, which are, well, at the time they were at the level of 0.8 electron volt, they are now slightly better. Now, the second technology that I talked about yesterday was Project 8, based on cyclotron radiation spectroscopy. Here, the idea is you have your gas molecule, so that's again tritium, and you have a magnetic field applied here. So there are magnetic field lines, and the electrons start spiraling around those magnetic field lines. And by doing that, they emit synchrotron radiation, which are then picked up by antennas that are basically located around the detector. And from the energy of that synchrotron radiation, you can learn something about you can basically measure the velocity and thereby the energy of the electron. Here is a first result from a Project 8 prototype. What's shown here in this kind of waterfall diagram is on the horizontal axis time, and on the vertical axis the frequency of the synchrotron radiation. So you see here at some point the trajectory starts, so that's the point when the tritium atom has decayed. Then, as it evolves over time, the frequency increases ever so slightly. That's due to the electron slowing down. Then sudden jumps happen. This is whenever the electron collides with a gas molecule. And then after each collision, you have again this slope here reflective of radiative energy losses. And from the starting point here, you can infer the energy that the electron started with. Now this was for a single electron, but of course in order to collect statistics, you have, ideally you have an Avogadro number of electrons simultaneously in your detector. And that clearly makes it very challenging to analyze this data. Okay, that's all the slides I wanted to show for today. Do you still have questions about neutrino masses, double beta decay, neutrino mass measurements, basically the topics that we talked about yesterday? If that's not the case, then let's switch gears to neutrino oscillations. And turn off the projector. Okay. So neutrino oscillations. The starting point for neutrino oscillations is again the Lagrangian that we had talked about yesterday. So let me quickly repeat it. There was the sum over flavors E mu tau. Inside there was the kinetic term of the neutrinos, nu alpha L bar ID slash nu alpha L. The term describing the charged current interactions, W mu dagger, nu alpha L bar, gamma mu E alpha, plus Hermitian conjugate. Then there was the neutral current term, G divided by 2 cosine theta W times Z mu, nu alpha L bar, gamma mu, nu alpha L. And there was the mass term, which, so I'm going to write down a generic Majorana mass term here, but for oscillation physics it doesn't matter. So 1/2 m alpha beta, nu alpha L charge conjugate bar, nu beta L plus the Hermitian conjugate. Right. Now, as we already discussed yesterday, this matrix M alpha beta is in general off-diagonal. When we discussed the seesaw mechanism, we had done this with only one neutrino flavor, but of course this can be generalized to 3 neutrino flavors. And then in principle, every neutrino flavor can couple to every other flavor here. So this is in general an off-diagonal matrix. And that means in order to determine the physical neutrino states, those with definite mass, this matrix needs to be diagonalized. So M alpha beta is in general off diagonal. And the way to do this is to perform a rotation in flavor space, so in the 3-dimensional space spanned by these dimensions E, mu, and tau here. And if I do this in such a way that M alpha beta becomes diagonal, then of course I need to do the same rotation up here in the interaction terms. For the neutral current interaction, it doesn't matter because I perform a rotation here on nu alpha L and I perform the opposite rotation on nu alpha L bar, so the transformation matrix cancels out. For the charged current operator, however, it stays because there's only one neutrino field here, so only that one gets rotated, this one does not. So the charged current interaction, which is diagonal in the flavor basis, right? There's alpha here and alpha there, will no longer be diagonal once I've gone to the mass basis. So let's do this. So to diagonalize M alpha beta, we write nu alpha L as U alpha J times nu J, where I've used the term already, but this is what we call the flavor states, and this is what we call the mass states. Or rather, I should say, this is the field in the flavor eigenbasis, and this is the field in the mass eigenbasis. And this matrix U is, of course, chosen in such a way that the matrix becomes diagonal. So that means U transpose M U should be a diagonal matrix with the 3 neutrino mass eigenvalues on the diagonal. Note that this is U transpose here, not U dagger, and that has to do with the charge conjugation here. Remember, charge conjugation is something like I gamma 2 times psi star, and then the bar implies another star, so there's no complex conjugation here. There's only a transposition, no complex conjugation. So I have to diagonalize the matrix with the transpose, not with the dagger of the of this U matrix. And well, that in turn implies that M alpha beta, by the way, has to be a symmetric matrix. It can be a complex matrix, but it has to be a complex symmetric matrix. And in fact, if there was any antisymmetric component to it, that would cancel out between the mass term and its Hermitian conjugate. Okay, let me write this down because it's non-trivial. So M alpha beta has to be symmetric, but can be complex. Any non-symmetric component cancels between the mass term and its Hermitian conjugate. And it's H dot C dot. Okay, note that this is something that would work differently for Dirac neutrinos. So for Dirac neutrinos, there would be different fields here, not a field and its charge conjugate, but left-handed and right-handed fields. So then the diagonalization would work the same way as in the quark sector. So note for Dirac mass term of the form sum over alpha beta nu alpha L bar M alpha beta N R beta. This would be different. Because there what we would do is we would transform nu alpha L to some u alpha j nu j, and simultaneously we would also transform the right-handed fields with some other matrix V beta k times nr k. And then the diagonalization would then imply that U dagger times M times V has to be diagonal M1, M2, M3. That's the more familiar way of diagonalizing a mass matrix. That's how we do it in the quark sector, for instance. But here we have two matrices, so it's a singular value decomposition effectively. And that also means that in the Dirac case, there are no restrictions on the mass matrix. It can be a general 3x3 complex matrix. So M can be a general complex 3x3 matrix. Okay. So now let's assume that we have transformed our mass term one way or another. And let's talk about what this means for the interaction term. So this means in the mass basis, the interaction term becomes so there is again the coupling constant g over square root 2. There is of course the W field. Now the neutrino field is now written in terms of the mass eigenstates, so nu j left times u alpha j star times gamma mu times E alpha left plus Hermitian conjugate. And the neutral current term is left unchanged. So G over 2 times cosine theta W Z mu nu J L bar gamma mu nu J L. And in all of this, there is a sum over J and alpha. Right? So in the neutral current term, I transform the field here with U and the field bar with U dagger. So U dagger cancels. For the charge current, I only transform the neutrino field. So here, this transformation matrix now becomes physical. And what that means in practical terms is that for a charge current interaction, in which, for instance, a nucleus decays, producing a charged lepton and a neutrino, what is effectively produced is a superposition of these three mass eigenstates. So this means a CC neutrino interaction produces a superposition of nu1, nu2, nu3. Okay, and that's the basis for neutrino oscillations. Now, to show you how exactly it leads to neutrino oscillations, I want to first show you the derivation that you find in most textbooks, which is based on simple quantum mechanical arguments, and afterwards I will show you how you can get the same result using a more QFT-inspired language. So, let's see, let's call this 2.1, neutrino oscillations in quantum mechanics. So in that language, we assume we have some sort of neutrino source that produces a neutrino together with a charged lepton. Can be a pion decay, can be a nuclear decay. And we write this initial state as a superposition of mass eigenstates. So we have an initial state nu alpha, which we write as u alpha j star nu j. Okay. One point that sometimes causes confusion is in the Lagrangian over here, I have, or rather in the transformation of my fields, I have a u alpha j. Why is it a u alpha j star here? Do you have an idea where the star is coming from? So why do the fields transform with u alpha j and the ket states transform with u alpha j star? Any suggestions? Think about how you get that state from the field. How in general do you get a one particle state in QFT using the field operator?
You apply a creation operator which has a dagger on it.
Exactly, you apply the creation operator, which is essentially the daggered field. And therefore, you use the daggered field and that turns the UAJ into a UAJ star. That's exactly right, that's where the star is coming from. Excellent. So now let's time evolve that state. That means this is now turning into a state which I call nu alpha of t and L. So after propagating over a distance t, over time t and a distance L, I now have a state u alpha j star times e to the minus I ej t plus pj L times nu j. And in both expressions, of course, the sum over j is always implied, but I can also write it out explicitly. So as usual in quantum mechanics, we evolve a state in space and time by multiplying it with a complex phase factor of this type. And notice that the energy and the momentum now have indices j, because the different nu j have slightly different masses, so slightly different kinematics. So I need to include an index j here. And this is also the reason why I need to go to the mass basis to describe the propagation of the neutrino. In the flavor basis, the neutrino doesn't have a definite energy and a definite mass, therefore I can't assign it a definite energy and momentum, and therefore I would have difficulty writing down anything like this. That's why I'm going to the mass basis. Now we imagine that we detect the neutrino, and we imagine that we detect it as a nu beta, which we again decompose into its mass eigenstate components. So u beta k times nu k. I'm writing this as bra vectors right away. And that means that overall the transition amplitude is nu beta nu alpha of t, which is u alpha j star, u beta k, u beta j. I'm already using the orthogonality of nu k and nu j here, so this gives me a non-zero contribution only if j equals k. And there is the complex phase factor ejt plus pjl. Okay. Then, to go from there to a probability, we square this amplitude. So the oscillation probability to go from a state alpha to a state beta is, let's call this A alpha beta. So it's A alpha beta modulus squared, which yields now a product of 4 mixing matrix elements: U alpha j, U beta j, U alpha k, U beta k star. And now I have here an e to the minus I ej minus ek times t plus I pj minus pk times L. Okay, so far so good. Now, the next step one does is one would like to get rid of the independent time and space dependencies using the fact that effectively neutrinos propagate at the speed of the light, so t and L are essentially similar. But one has to be a bit careful in doing this, otherwise one gets a factor of 2 incorrect. So the way it's normally done is that one argues that in a typical neutrino source, we do not know exactly when the neutrino is produced and when it is detected. We know only where it is produced and where it is detected. It's true that we do have some timing information in a realistic experiment, but typically that timing information is inaccurate enough that the approach I'm going to take now is in fact justified. We can talk about the subtlety more if you like. So what we are going to assume is that the source is quasi-stationary and that means we integrate over capital T over the time. So we write the probability as 1 over some normalization factor, which we are effectively going to determine in the end by the requirement that this should have the properties of a probability. So I'm not going to spend much time on determining it beyond that. Integral dt times the p alpha beta from before. So that is 1 over the normalization factor. And then if that integral, if I can extend the integration region sufficiently far that I can approximate it as minus infinity to infinity, it gives me a delta function, delta ej minus ek. In principle there is a 2 pi, but it doesn't really matter because I'm going to absorb all of this into the normalization anyway. And then we have again our 4 mixing matrix elements, U beta j, U alpha k, U beta k star, e to the I pj minus pk times L. And for this to have the properties of a probability, this means that if I sum, let's say, over beta, it has to add up to 1. Or if I sum over alpha, it has to add up to 1 as well. That's simply the statement that if I start with a new alpha, well, it has to oscillate into something. So it has to end up in one of the 3 possible final states, either nu e, nu mu, nu tau. So if I sum over all possibilities, I need to get 1. And by that requirement, I determine the normalization constant, and that means that I effectively set all of this prefactor to 1, including the delta function. I can do this because this is never an exact delta function, right? Realistically, time never runs over an infinite interval, so this is always an approximate delta function. And that means I can cancel it against an appropriate factor inside my normalization constant. Now, there are a few subtleties here that people usually brush under the carpet, but I still want to mention at least one of them. So the way I've written this here is I have assigned each neutrino a definite energy and a definite momentum. Why do you think that could be problematic? Come on, don't leave me alone with my problems. What exactly do you mean? You said you cannot assign a position that goes in the right direction. What exactly do you mean by this?
By the uncertainty principle.
By the uncertainty principle, right? So I only know where I produce my neutrino with a certain accuracy. But I do know it to some extent. For instance, if I say I have an experiment like Dune, where I produce my neutrinos at Fermilab and detect them in South Dakota, I roughly know where Fermilab is and I roughly know where South Dakota is. And that means I have at least some position information, and that means I cannot have infinitely precise energy information. And that is indeed what rescues neutrino oscillations. Because if I knew exactly with what energy and what momentum my neutrino is emitted, well, by knowing the energy and the momentum, I can calculate the mass. So with that information, I would know which mass eigenstate is propagating. And that means there could not be any interference. And so what rescues neutrino oscillations is in fact the uncertainty principle. Only because my knowledge about the neutrino's energy and momentum is not perfect can the different mass eigenstates interfere. So different mass eigenstates can interfere in this way. Only because EJ, or let's say only because the Heisenberg uncertainties are much larger than the difference between EJ and EK and the difference between PJ and PK in realistic situations. Right. So that's an important point. So if you want to describe neutrino oscillations really correctly, taking all of this into account explicitly, then what you do is you describe your initial state not in this way, but you describe it as a neutrino wave packet, so as a state that is a superposition of states with nearby momenta with a certain shape factor, like a Gaussian shape factor or a Lorentzian shape factor. It doesn't affect the oscillation probability, but it adds extra factors to it that describe the conditions under which oscillations disappear. So it describes decoherence. And then if you put in numbers, you realize that these terms are not relevant in realistic situations. Okay. Now, that's the derivation of neutrino oscillations that you find in most textbooks. What I would like to do now is I would like to derive the same using a more QFT-inspired approach. So that's 2.2 neutrino oscillations in QFT. And by that I mean we're effectively going to evaluate a tree-level Feynman diagram, which is no different from other tree-level Feynman diagrams, except for the fact that in the intermediate state we have a neutrino that propagates over a macroscopic distance. So our amplitude in QFT is going to be given by the following sum over diagrams. Well, let's consider a typical experiment where I have, say, some nuclear decay here. Up quark goes to down quark, goes to W, goes to a charged lepton. So let's call this an L alpha. It goes to a neutrino, and that neutrino now propagates over a macroscopic distance, ideally in a straighter line than what I've drawn here. And I'm taking this neutrino to be a mass eigenstate nu j. Once again, I need to go to the mass basis to describe the propagation, for the simple reason that I only know how to write down a fermion propagator with a definite mass. And then here on the detection side, we assume that the neutrino interacts by again producing, say, a charged lepton. And I realize I drew my arrow here the wrong way. So let's say this is a nu alpha plus and this is an L beta minus. There's a W, and let's say it converts a down quark into an up quark. So the process described over here, this is the neutrino source. Over there is the detector. And these are processes that happen over microscopic scales. Whereas here in the middle, I have the propagation over a distance L, and that is macroscopic. Okay, now the advantage of taking this approach is, in a sense, I never need to worry about what state my neutrino is in. I need to worry about the states of my external particles, but they at least have a definite mass. So there's no mixture between different particles here on the external legs. The only place where the mixture happens is the neutrino, and the way it's taken into account is by summing over all possible diagrams that contribute to the process with the given external states. So that's the sum over J. Okay, and now we just apply the Feynman rules. So that gives us a sum over J. There is an integral d4x. So I'm writing down the Feynman rules in the coordinate basis, not in momentum space. There's an integral d4x over the source. So what I mean by this is that I'm not integrating over an infinite region of space-time, but I'm integrating over a region that is about as large as the uncertainty in the localization of my production process. I have a similar integral over the region in which the detection process is localized. So in a sense, I'm integrating over the position of this vertex x and over the position of that vertex y. I'm writing down the expression for the fermion line. So the fermion line reads U bar L beta, so that's the spinor for this guy. Let's call this momentum P beta prime, e to the I P beta prime y. That's essentially the wave function of this external particle here. So the momentum that's going out here is what we call P beta prime. Then I have my neutrino propagator, which involves an integral d4p over 2 pi to the 4th. P nu slash times e to the minus I p nu. And now here I have y plus L minus x. And in the denominator I have p nu square minus mj square plus I epsilon. So that's now the most crucial part of this amplitude. What you notice is, first of all, I've neglected the neutrino mass in the numerator, because in the numerator it doesn't matter. It's totally negligible compared to the contribution from the momentum. Regarding the distance that the neutrino travels here, I've defined my x and y in such a way that the source is localized around x equals 0 and the detector is localized around y equals 0. So the distance between the two is included here explicitly by this L. And here I'm abusing the notation a little bit. What I mean by L here, that's of course still a 4 vector. So that's the 4 vector basically given by the time and the direction vector. So what I mean by this is t, comma L. Right, and then all that's missing is the spinor for the antiparticle over there. Oh, and I forgot my vertex. I forgot the vertex. Right, that's important. So there's a gamma mu u beta j here. And there is a gamma nu u alpha j star from the production side. And there is the antiparticle spinor v alpha p alpha times e to the minus I p alpha x. So that means the momentum that's outgoing here, that's what we call p alpha. Okay, then everything contained in these hadronic lines I'm going to absorb into hadronic matrix elements, which I call simply M mu source and M mu detector, and I'm not going to worry much about those. And finally, the only thing I need, because it will be important for the vertices, is that from the W propagators, I'm going to have a factor e to the I pw prime y times e to the minus I pw x. So there's a momentum pw prime flowing here, and there's a momentum pw flowing there. And everything else related to this interaction is absorbed into the matrix elements.
Would you mind writing a bit bigger? We can see
Sorry, writing what bigger?
Yeah, please.
Yes, I will do my very best. Sorry. Okay. So the first thing we're going to do is we're going to carry out the x and y integrals. The only places where x and y appear is in the phase factors. There's a y here, there's one there, and there's one there. And x appears here, here, and here. So if those integrals were running over an infinite domain, then these would simply be delta functions. Now, because they are running over a finite domain, they yield only approximate delta functions, which I'm going to write as delta hat. So let's see. I'm going to pull out the mixing matrix elements, U alpha j star U beta k. I'm also going to pull out the nuclear matrix elements. So M mu source, M mu detector. I retain the four momentum integral, d4p over 2 pi to the fourth. And I should call this dp nu for consistency, but that's really just the momentum that's flowing here in the neutrino line. So that's what we call p nu. So now come these approximate delta functions. So let's call them delta hat of, let's see, the one from the detection side gives us p nu minus p beta prime minus pw prime. And the one from the production side gives us p nu minus p alpha minus pw. So, as I said, these are approximate delta functions. With a width similar to the uncertainty, or let's say the size of the source and the detector inverse. Okay, and we are going to leave them like this and then get rid of them in the end. Sorry?
When you want to then later evaluate this expression, do you use these approximate delta functions as normal delta functions?
I cannot use them as exact delta functions because by doing that I would effectively assume that I know exactly my neutrino momentum, and that would break the interference. We'll see that in a bit, how I deal with them. So now let me first make sure I'm not forgetting to write down the remaining terms. There are still the spinors. U bar beta, I'm shortening the notation here a bit, so I'm omitting the explicit momentum dependence, and what I call UL beta here, I'm just going to call U beta. Gamma mu, then my propagator leaves me p nu slash e to the minus I p nu L. Notice that that part has not been absorbed into any delta function, so that one I need to retain. And the denominator of the propagator is still p nu square minus mj square plus I epsilon, the gamma nu from the second vertex, and the V alpha for the antiparticle spinor. So the next step is to evaluate the momentum integral, and I start by evaluating the integral in P0. And now I'm explicitly not using any of the delta functions to help me, but what I'm going to do instead is I'm going to use complex contour integration. So I basically want to use the residue theorem. for the p nu 0 integral. So if I look at the analytic structure of my integrand in the complex plane, so if I draw here the real part of p nu 0 versus the imaginary part of p nu 0, then I have one pole over here and one pole down there. The expression in the denominator of the propagator can be written as p nu 0 minus square root p nu vector squared plus mj squared plus I epsilon times p nu 0 plus square root p nu squared plus mj squared minus I epsilon. Well, because if I evaluate this, I get a p nu 0 squared minus square root p nu square plus mj square minus I epsilon square, which is p nu 0 squared minus p nu vector squared minus mj squared plus, well, let's call this I epsilon prime, where I epsilon prime is effectively this square root times I epsilon times 2. So this is 2 times the square root times epsilon. And of course, I'm from now on going to call epsilon prime and epsilon the same thing. Okay. But so what I'm going to do, given this factor here, I see that I need to close my contour in the lower half plane, which means I'm going to pick up this pole here, and that means I can replace the integral by 2 pi I times the residue at this pole. So this means that my amplitude is proportional to, well, the first line, the first pieces here are simply copied. There are the usual matrix elements, U alpha j star, U beta j. There are the 2 hadronic matrix elements, which I simply copy as well. There is an integral d3 p nu left over 2 pi cubed. And now under the integral, we have, well, we have the U beta bar spinor. Oh wait, let me first write down the approximate delta functions. They of course stay as well. So delta p nu minus p beta prime minus p w prime, delta hat p nu minus p beta p alpha minus p w. And what's left of my propagator is u bar beta, gamma mu, p slash nu divided by 2 e nu j. And that quantity is now defined as the energy corresponding to this momentum here. And I retain a complex phase factor minus I E nu minus P nu, E nu T minus P nu L times gamma nu times V alpha. And this is again E nu J, which is just the on-shell energy. So that means square root vector p nu squared plus mj squared. Okay. So what you see is that what's left of my propagator is essentially a phase factor that looks very much like the phase factor that we had multiplied in the quantum mechanical approach to neutrino oscillations to account for propagation. Right. So, and what we've exploited here is that our propagation distance L, we've assumed that to be directed in the direction of the momentum p nu, which means we consider only forward propagation. We do not consider the contribution from antiparticles propagating backward in time. That's effectively where we have used the fact that the propagation is occurring over a macroscopic distance. So that's different from what we do when we consider processes that happen entirely in the microscopic domain, right? Then both forward propagation of a particle and backward propagation of an antiparticle contribute to the propagator. But the second case we've explicitly dropped here. Otherwise, we would have would have two contributions, one from each of the two poles. Okay. So now we need to talk about this phase factor there in the numerator. So consider this phase factor. Let's give it a name. Let's call it phi of p nu. But by this I simply mean E nu j times t minus p nu j times L. I should have been more careful here and not forget the vector on the L. So the first thing I'm going to do is I'm going to use the fact that neutrino masses are small, which means I can expand this. So I can write this as vector p nu times vector p nu divided by modulus of vector p nu times t minus L plus a term that contains the mass divided by 2 p nu times t. And by p nu here, I mean, of course, simply the modulus of the vector p nu. Okay, so the second thing we are now going to talk about again is these approximate delta functions. So remember that these delta hat functions, they have a width comparable to the inverse size of the source and the detector. So let's call this sigma s or d. So the size of the production detection region. And this, of course, now depends on exactly what process is making our neutrino. But very roughly speaking, these processes are typically localized to within, say, an interatomic distance or so. For instance, imagine you have an atomic nucleus decaying somewhere inside a nuclear reactor, for instance, then that nucleus is typically localized to within an interatomic distance. So that's similar to an inverse angstrom, and in energy units, that's similar to order keV. And that means that terms which vary slowly over such momentum intervals can be pulled out of the integrals. So that means terms that vary slowly over such momentum intervals can be pulled out of the integrals. Okay, and that's the case in particular. Well, I've already pulled out the nuclear matrix elements, but also here the prefactor and the propagator, for instance, or the spinors. These are all relatively slowly varying functions of momentum. So these are all objects that I can pull out of the integral. So that means, let's write this out again. So I have my amplitude, which is proportional to u bar beta, gamma mu. The prefactor from the propagator, I'm going to call this p nu slash 0 divided by 2p nu 0. And what I mean by this is it's a momentum that's basically roughly on the order of my PE plus PW. So that's the, let's say, rough neutrino energy, not taking into account small differences because of neutrino masses. But because it's only a prefactor, those small differences don't matter. They will be a higher order and can be neglected. Then there is a gamma nu. There is the spinor for the antiparticle on the production side. There are the nuclear matrix elements, m nu s, m nu d. And well, as I said, I'm making a small mistake here by taking this kind of average neutrino energy. So I'm dropping here terms that are of order mj square over p nu 0 squared. Then I have my sum over j, u alpha j star, u beta j. And now I have my 3 momentum integral with the remaining terms, those that are not slowly varying. And that is in particular the exponential, the phase factor, minus I e nu j times t minus p nu times L. And I have the 2 approximate delta functions. So I'm just going to write this as the 2 approximate delta functions. So there's one annoying aspect is that these are still vectors here, right? In principle, I'm still including here cases where the vector pointing from my source to my detector is not aligned with the direction of propagation of my neutrino. And I'm now going to argue formally why I can drop this and turn this just into from a vector dot product into just a product of scalars. So for that, so to turn p nu dot L to something like p nu L, we use the method of stationary phase. which basically says that if you have an integral that looks something like integral over some variable x, there's a function f of x times e to the I times phi of x. And this function f, this is an arbitrary function. And we call delta x the interval over which this function varies significantly. Call delta x the interval over which f of x varies significantly. So there's a typical scale associated with that function, a typical scale over which it varies significantly. So this integral can be large only if phi of x has order 1 variations only over intervals larger than delta x. Because otherwise, so if phi was oscillating more quickly than f is changing, then the integral would simply average f to 0. So otherwise, fast oscillations of phi, or fast oscillation of the exponential of e to the I phi of x would average the integral to 0. So graphically, if you imagine your function, let's say we have some function here, and there is an envelope which is given by f, and the fast oscillations here are due to phi. Then if these oscillations are fast enough, then you can intuitively see that that would average the integral to 0. So we want the oscillations of phi to be as slow as possible, and certainly slower than the variations in f. And that means that the main contribution to this integral is going to come from configurations where phi is at a minimum, so at a stationary point, hence the term stationary phase approximation. So this means, so the main contribution will come from configurations where variations in phi are minimized. And for us, this implies that we can demand that P nu is parallel to L. Because if it wasn't, then, so imagine we are looking at kinematic configurations where P nu and L are at an angle to each other. Then the second term here in the phase factor always has some cosine of that angle in it. So that means there can never be an approximately exact cancellation between the term depending on energy and the term depending on momentum. Whereas if P nu and L are aligned with each other, then that overall phase here can be very small can go to 0 at the point where t and L are basically identical. And using that, we have now at least turned our three-dimensional integral into a one-dimensional integral. There are some order 1 factors that arise when I do this, but I only have a proportionality sign here, so I don't care about those. I'm anyway going to determine the normalization in the very end, again by the requirement that the probability has to behave like a probability. Okay, so that means I'm going to turn this integral into a 1D integral now. And there are no further simplifications I can then make at the level of the amplitude. So let's now immediately go to the probability. So the probability P alpha beta, which is the amplitude squared. Times some, let me again put in some normalization constant here, which we are going to determine by the requirement that the probability has to behave like 1. So that is 1 over the normalization times, now because I have squared it, I have a sum over j and k. I have the 4 mixing matrix elements, u alpha j star, u beta j, u alpha k, u beta k star. I now have integral dp nu, integral dp nu prime, so one coming from A, one coming from the complex conjugate of A. I have the 2 complex phase factors, so e to the minus I Ej minus Ek prime times T minus P nu minus P nu prime times L. And just to make clear what I mean by these energies, so Ej, this is square root P nu square plus mj square, and Ek prime, this is square root P nu prime square plus mk squared. Well, okay, and now I have 4 of these annoying approximate delta functions, so I have no choice but to write them down all 4. So P nu minus P beta prime minus PW prime coming from the detection vertex. Delta hat of P nu minus PW minus P alpha coming from the production vertex. And then the same again, but with P nu prime instead of P nu. P nu prime minus P beta prime minus PW prime times delta hat P nu prime minus PW minus P alpha. So now we make again, similar to what we did in the quantum mechanical approach, we make the assumption that we have a quasi-stationary neutrino source, which means we're going to integrate over the time capital T. So let's assume a quasi-stationary source. And once again, for cases of practical relevance, one can look at the numbers and show that this is a good approximation. So assume quasi-stationary neutrino source. So that means, so I'm going to be a bit sloppy here with the notation. In principle, this is now no longer the same quantity as before, so I should call this something like p bar or so, and also the normalization constant is now going to be a different one, but I'm going to abuse the notation a little bit here and still call it p and n. So this is a slight abuse of notation. But I don't want to carry along too many bars and twiddles and so on. So integral dt a squared. So now we're going to use this integral in dt with the first part of the exponential phase factor to get a delta function, and we're going to use that delta function to get rid of one of the momentum integrals. Because those momenta here, right, this is essentially the same as integrating over dE nu, and this is essentially the same as integrating over dE nu prime. So I'm going to get rid of one of the momentum integrals this way. The rest remains. There are the usual 4 mixing matrix elements, U alpha j, U beta j, U alpha k, U beta k star. There is that one energy integral that's left. What's left of our phase factor is square root E nu square minus mj square minus square root E nu square minus mk square times L. And I still have the 4 delta functions. Which I'm not going to write out explicitly again. So now we use a Taylor expansion in the phase factor. So we use that square root E nu square minus mj square minus square root E nu square minus mk square times L is approximately equal to minus mj square minus mk square divided by 2 E nu times L, and usually we call this minus delta m jk squared times L divided by 2 E nu. So that's basically the definition of this quantity delta m jk square. It's just mj square minus mk square. Now, why am I doing this? Now here the numerator has a very small number in it, namely the difference of 2 neutrino masses. So that means that because I have this difference here, my phase factor is now slowly varying over distances corresponding to the width of these delta functions. And that means I can pull those delta functions out of my integral. No, I can't. No, I don't pull the delta functions out of the integral. I'm pulling the phase factor out of the integral. Sorry. So, so this varies slowly. Over intervals of width delta E nu similar sigma s d to the minus 1. So similar to the inverse size of my source and detector. So that means I can pull the phase factor out of the integral. So now I have everything that depended on the properties of my neutrino gotten out of the integral. All that's left is an integral over these annoying deltas, but because these annoying deltas do not depend on J, for instance, they do not depend on the neutrino mass eigenstate, I can simply say, okay, whatever they are, I'm going to absorb them into the normalization constant. And that's how I'm getting rid of them. So, we absorb the remaining integral dE nu over those deltas into the normalization. And the normalization is chosen such that for instance, sum over beta, p alpha beta equals sum over alpha, p alpha beta is equal to 1. And that means that the residual integral that I have left just cancels against whatever this normalization constant is. So that means I end up with a probability p alpha beta, which is sum over j and k, u alpha j star, u beta j, u alpha k, u beta k star, e to the minus I delta m jk square times L divided by 2 times the neutrino energy. And that is exactly the same result as we had obtained before using just the quantum mechanical derivation. Okay. So that's basically the end to today's lecture. Just as a recap, we've talked about neutrino oscillations by starting with the observation that neutrinos' flavor eigenstates are mixtures of mass eigenstates. We have then first argued, just based on quantum mechanics, that, well, because different mass eigenstates propagate slightly differently, then as long as they can interfere with each other, there is a non-zero probability for neutrinos to convert from one flavor to the other. We have then rederived the same result, but now using a QFT language. We have written down a Feynman diagram that described the combined process of neutrino production, neutrino propagation, and neutrino detection. And then we have evaluated that in that diagram. The main steps along the way were that we have evaluated the propagator over macroscopic distances by dropping the piece that corresponded to the propagation of antiparticles backwards in time. So in that sense, we have forced the neutrino to be on shell because it propagates over long distances. That has shown us that in that case, the propagator has reduced to something very similar to the phase factor that described the propagation in quantum mechanics. And then we've had to do a few extra steps to massage our integrals, to get rid of kinematic configurations where the neutrino is not propagating from the source to the detector but at an angle, and all the prefactors that we've pulled along the whole time have in the end been absorbed into a normalization constant. And with that being done, we ended up with the same result as in the quantum mechanics approach. And that result, it shows the interference between mass eigenstates because there's the sum over j and k. There is for j unequal k, there is the interference terms, and they are weighted with these products of mixing matrix elements. And to make this more concrete and more phenomenological, that will be then the topic for tomorrow. Thanks a lot.
Quick questions for Joachim.
When you did the contour integral, at that point of time in the numerator you had these like delta hats, right? And the delta hats depend on P nu. So when you do the contour integral, shouldn't you plug in the value of the pole in these delta hats?
Yes.
And even after you do that, you do all these arguments, the delta hat magic at the end still works out.
Yeah, so the delta hat, you remember the delta hat had a 4-vector P nu. So what I did not write out explicitly was that after doing the complex contour integral, that 4-vector reduces to an on-shell 4-vector. So the energy component of that vector is now determined by the momentum components. And then after that, with the thus constrained delta hats, I'm then doing this step here where I pull everything else out of the integral and I retain only the integral over the delta hats and I cancel it against the normalization factor.